So moving on to the proofs. So to prove sufficiency, we start with the Spence-Murley's condition. So by a standard static mechanism design argument, we can show that the Spence-Murley's condition would imply Q being implementable, and and by some small amount of algebra, we can show that the single crossing condition, the PST condition, implies that the Z or the marginal incentive functions are increasing, and the marginal incentive being increasing, implying the difference between the value function and utility function being increasing, in turn implies that the Qt is implementable. This part is given in KS. So what I did here is very small. So all I did is a small amount of algebra that proves that the single crossing condition is equivalent to the Z being increasing. So for the converse, the necessity part, so it's similar. So implementable, go back to imply the Spence-Murley's could be done by a standard static mechanism design argument as well. So in the Cruz and Strack paper and in the PPST, they do not have the converse. So I prove all these three. So first, Z being increasing imply this is a small amount of algebra as before. Also, this difference being increasing implying Z being increasing is a small amount of algebra as well. So the main thing is here. So the implementability implying this difference being increasing. So the argument can be seen very easily graphically as well. So if it's not increasing, so if it's decreasing at some point, so say the V is decreasing at some point, then it's impossible to implement something in the middle. So if we want to implement something in the middle, on the right, we should stop. But on the left, the problem is we have part continue, and this part we will stop as well. So this thing will not be a single cutoff rule, but tau here is a single cutoff rule. So by some argument like this, we would show that this thing must be increasing everywhere. So until this point, it seems that there is not really a lot of contribution. So that would be why I go on to do the binary cutoff rules. So before I start the binary cutoff rule, so ideally binary cutoff rule would come from some kind of convexity condition. So the utility function ideally would look like this, but I tried this, but it doesn't really work. The condition looks really complicated. So I cheated a little bit. What I did is I assumed that this kind of shape come from two utility functions. One is the utility function from one type of allocation. So I could call it the plus type. So it's increasing. And the other one comes from the other type of allocation. So it's, you say, U minus here. And then to simplify the notation, I call Qt can be both positive or negative. If Qt is positive, then it's the positive type, and Qt is negative, then it is the negative type. So the max of these two would have this kind of concave shape that we wanted. So the conditions are the same. So we still have the Spence-Murley's condition on both types of allocations, and similar thing happens with the PST conditions. So the main result is exactly the same. These two conditions are sufficient and necessary conditions for implementability of all binary cutoff rule here. So the only thing that's changed is the binary cutoff rule. However, the proof is a bit more complicated because the main thing is that the monotonicity of Z alone would not imply the monotonicity of the difference between the utility function and the value function. So that's the main difficulty. So as before, the Spence and Murley's condition implies implementability, and they also imply the monotonicity of the utility function. So the utility function is not the original utility function. Here is the utility function after the terminal Qs are implemented. So after they are implemented, they must be monotonic. And something that I found is that combining the monotonicity, so say say for the plus side, combining the monotonicity of Z and the monotonicity of the U, combining these two, I can get the difference between the stopping value and the value function being monotonic. So the other one does the same. So combining these two, I can implement any binary rule. So basically, if both U and Z are monotonic, then we have one side of this being monotonic, and the other one would look like this. Then if we cut a zero, then we have a binary stop rule. So the converse or the necessity looks the same. So Q being implementable would, as before, would imply the Spence condition, and also they would imply the monotonicity of the utility function. So as I said, these two things are not equivalent to each other. So I need this one plus the monotonicity of U, which comes from the implementability of Q's. I need these two together combined to get one of the set being monotonic. So after having that result, given the monotonicity of the Z's, then I can go back and prove that the single crossing condition holds. So basically, the single crossing condition is equivalent to the Z being monotonic, and to prove that we need both the utility function and the difference between the utility function and the value function being monotonic. So I stated another example here. It's the advice example from before. So suppose we have actually two possible actions after we stop, and also we assume that this xt is a martingale. So if both of these are true, and if we assume we have linear utility functions, so from one type of action we get some constant utility which is smaller than zero, and from the other one we get a positive constant utility, then we have all of the binary cutoff rules are implementable. And also there is a closed form formula, some modified version of a closed form formula from the Cruz and Strack paper. So the proof here would rely on a lemma that says if we have the stochastic process is martingale plus it has monotonic transitions, then it preserves the bounded derivative property. So if V has derivatives that are bounded by two constants, then the expectation of V, given the previous one, so Vt plus 1, would still have bounded derivatives. So from this thing, we can show that the ZTs are monotonic, and then applying the theorem, we can get the